SwayamPrabha. Digital India. Educated India.
Welcome to today's lecture. In the previous lecture we talked about the tab model and we showed that how the tab model is basically a 1 degree of freedom model in which the droplet actually oscillates, but in a unidirectional manner and it breaks up when the north pole and the south pole of the droplets actually merge, and you get 2 dotted droplets, and we also found out how you can get the velocity and the sizes of these dotted droplets. But as we said that the tab model was only valid for a low wave number range, basically between 0 to 11 or 1 to 11. Okay. And but in most of the cases for large wave number, whenever you have this multimodal kind of a breakup or catastrophic mode of breakup, you actually experience waviness or waves develop on the droplet surface. Okay. And the tab model is not a useful model for that, because it is no longer a single degree of freedom system at all. Right. In this situation one needs to do a linear rigorous stability analysis, and basically through that stability analysis what we try to find out, as we explained in the last class, that there are waves that are created on the surface. How fast does these waves grow? Which are the waves that actually grow to such an extent that it might actually atomize the liquid? Okay. So, that is the thing that we actually said. Now, if you recall, if you just look at the slide, you will find that in this particular case, okay, the most of the wave model is modeled basically on the Kelvin-Helmholtz type of a model. Okay, in this particular model, okay, what we take is that both the fluids were inviscid, they had a variation in density, there was a U1 and a U2, right. Now, any small perturbations like this, what we have created on the droplet surface is modeled like this. Okay. And we considered only the real part, okay. And if the real part, this is basically omega is basically the growth rate and lambda is basically the wavelength and k is the basically the corresponding wave number. So, if omega r is greater than 0, okay, that means the real part of the growth rate, the wave grows in time. If it is less than 0, it decays with time. Okay. So, that was what the thing that we covered in the last class. How do we get this? Basically we do it in 2 ways. One is that if you look at this particular equation over here on this, okay, you will find that we have written basically 2 equations, which is basically nothing but the momentum equations, right. But these are inviscid forms because you do not see any viscous terms over here anymore, right. So, I equal to 1 is basically the top fluid stop, and I equal to 2 is the bottom fluid. Okay. So, the other thing is that this is the boundary condition, this is basically across the interface, the pressure differential is given by the surface tension into the curvature. This we already did in the previous classes, right. Now, what we do is that the simple thing, as we learnt earlier, that your UI has got a base component, right, a base component, and there is a fluctuating component on the top of that. Your Vi only has a fluctuating component. So, if this is 4, this is 5, if we substitute them in these 3 equations that we have over here, okay, and in order to make a linearized version, one can show, and you can do the math yourself in your spare time, that the growth rate is basically given by this particular form, right. There are the 2 densities, there is the surface tension, the wave number, okay, the difference in the velocities. Okay. So, this is the complete form that you will get if you work from this equation, this set of equations, okay, with the corresponding interfacial boundary conditions. Now, as we said, when omega is greater than 0, okay, or the real part of the omega when it is greater than 0, okay, that means the second part of it, right, when it is greater than 0, okay, you will have a unstable situation, right. So, in this particular case the unstable situation can be written as this is greater than 0, Okay. So, if you do the algebra, you will find that the essential relationship boils down to this, where this part is basically represented as A, right. So, it means that when the k values, okay, are less than A, okay, where k, if you recall, was 2 pi by lambda, right. When this is less than A, there is always a growth of instability. Okay. So, any wavelength, all possible wavelengths which have value less than k less than A, okay, will basically intensify, right. Okay. So, this is basically the situation, that k less than A. Okay. So, and there of course will be a lambda for which the growth rate is maximum, that is called the maximum omega x, or the maximum growth rate. The lambda corresponding to the maximum wavelength determines the length of the ligament which detaches from the sheet. I will show that in this particular plot what happens. If you look at it here, so this is for example a liquid sheet like this, right. Okay. So, the liquid sheet is moving with a velocity, and then there is air that is moving also with a velocity. So, you get this ligaments, right, you get this waviness on the surface, and the ligaments detach and they subsequently break up with showing all these oscillations. Now, if you look at this situation, if you plot that omega versus that k that we were talking about, right, you will find that this is the maximum k for which the growth rate is maximum, right, for which the growth rate is maximum. Got it. So, this is what we meant when we said that over here the lambda corresponding to the maximum omega max, right, determines the length scale of the ligament which detaches from that sheet. So, that sheet that we showed, what is the length scale of the ligament that actually detaches from the sheet is determined by what is the lambda, or what is the wavelength, this wavelength corresponding to the maximum omega max. Got it. So, there are, so this, that wavelength is the strongest or the most dominant, right, as we saw in that particular dispersion curve, right. You saw that dispersion curve which looks something like that, right. So, in that particular dispersion curve, so you saw this, right. So, this is that omega, and the corresponding lambda gives you that what will be the detachment of the ligament that you will get out of it. That means the length scale of the ligament that you will get out of it. Okay. So, it is a simple linear stability analysis in visit conditions, okay, by which you can actually predict what will be the growth rate of the disturbances and what will result in the, what will be the resultant ligament diameter. Okay. Now, the previous equation was a more general form of the KH instability, does not include physical dimensions like for example, jet diameter and jet thickness. Now, if you want to solve for a liquid jet or a liquid sheet, okay, whatever is the case may be, like in the previous case we showed a liquid sheet. Okay. So, in this case all the dimensions have to be included to predict the most unstable wavelength, correct. Okay. So, like for example, in this case if you look at it, there is an inner diameter, there is an outer diameter, and there is some perturbations that are created on the surface like this. Okay. The jet has got an, or this cylinder has got an undisturbed, okay, liquid jet has got an undisturbed or unperturbed diameter of Ra and Rb. Okay. So, there are amplitudes of the disturbances on the droplet surface, on the jet surface. If this is a situation like this which Mayer did in 1987, you can write basically the governing equations for this, right, in a similar way that we did earlier, right. And you can also, this is the same thing, okay, you model the perturbation, the infinitesimal perturbation that is created in this particular form, where k is basically the wave number, omega is basically the growth rate. This is the same thing that we did in the previous one. Okay. Normally people use the potential function or the streamline or the stream functions. Okay, stream function, this is not streamline, this is actually stream function. Okay. So, stream function and the velocity potential, okay, to basically propose the solution. Now, if you see these I naught, well, the math is a little bit complicated. I naught and II are basically the modified Bessel's function, okay, and this particular relationship gives you the fluctuating gas pressure, You do not have to understand everything, but this is just a mathematical procedure, okay, and these are the corresponding linearized boundary conditions. Okay. So, this is basically the interface oscillation, V1 is basically the interface oscillation, right. Okay, the rate of change of that interface oscillation or the change in the distance of that interface. Okay. And so, based on this, these are the equations that you get. This is once again the similar type of equation that you would get when you actually have the interface across the interface. Recall that we already did this in earlier classes, this in earlier lectures, right. If you recall, this was done, right, when we wrote the generic condition across interface. We wrote the pressure and we wrote the surface tension and all those things, viscosity, everything we took care, right. So, that part should be well understood. If you have forgotten, you can go back and study that portion. Okay. So, this is what the typical dispersion curve actually looks like. If you look at this dispersion curve, once again it is the same thing. Okay. So, this is the corresponding K max, okay, the maximum growth rate that you will have. Okay. And once again the logic is essentially the same that we showed earlier. Okay. So, using these equations one can find, this is the most important part. So, this can predict what is the maximum growth rate that you are going to have. Okay. Now, this is very complicated, but you do not have to go through all the math. What is most important is that we can show that this relationship is valid. Okay. You can try it out, okay, and then ultimately these two relationships are the most important one. This is basically the wavelength and this is the basically the growth rate. Now, you can write it as omega, you can write it as lambda, whatever, does not really matter, okay. And this Ta that you see is basically Onsorge number Weber number combination, and where the two Weber numbers are given as that, Weber number 1 and Weber number 2, right. So, these two relationships enables us to calculate that depending on a particular Weber number and a particular Onsorge number, right, what will be the maximum wavelength, what will be the most optimum wavelength, right, that will lead to this kind of dispersion. Similarly, the maximum growth rate can also be predicted if you know the Weber number and Ta and the Onsorge number, right. So, all these things, all these numbers, this actually gives you what will be the growth rate and the corresponding wavelength, okay, for the most for the maximum growth rate and the most disturbing wavelength if you add it in that fashion, right. So, the resultant droplet diameter is more or less half of the maximum wavelength, right, the resultant droplet diameter. That means the diameter of the droplet will be somewhere around the similar value as this guy, okay. And similarly, the time scale for the breakup is given by that particular form, right. So, these three equations, this is 1, this is 2, this is 3 and this is 4. So, these 4 equations 1 to 4 gives you basically many things. One, it gives you the most unstable wavelength, right, unstable wavelength. It also gives you the max growth rate, okay. It also gives you the breakup time, that is important, okay. It also gives you the daughter droplet dia, right, okay. And all these informations you can get, these are your outputs, your inputs are Weber number basically 1 and 2, right, Onsorge number. If you know Onsorge number, Ta is basically a derived quantity, okay. So, if you feed these two values into what we call the black box, let us consider this to be a black box, right. So, it is like this. So, your input is like that, these are your inputs, then this is your linear stability analysis, right. So, that is the box and your output is all these things, got it, okay. So, the input is basically Weber number and Onsorge number, this is linear stability is the black box. So, we do some operations, we solve some equations which is basically nothing but still the governing equations, right, and using all those things you get an output which is basically nothing but the unstable wavelength, maximum growth rate, breakup time and dotted droplet diameter. So, even if you do not understand all the math, does not really matter, okay, because but you feel free to actually work out the math, right. So, but because of the interest of time we are not solving it, we are just giving you the key equations, okay, and how we actually derived it, right, the procedure essentially, and from there you can easily show that your main question through the linear stability analysis will be to determine what is the growth rate, what is the unstable wavelength, what is the breakup time, what is the droplet diameter, right. If you get all these 4 information, then the model serves its purpose, okay. That is exactly what we have done, and the input you want to cast it in such a way that the input becomes a function of your Weber number and Onsorge number, right. Well, not in all situations you will be able to get such clean quantities, but in most of the situations you can, and that is an interesting thing over here, okay. So, based on this there are other models also. So, if you look at it, okay, for secondary breakup. So, wave model is particularly useful for primary breakup also, as you saw, okay, and we will just have one more slide on this just to reiterate. The Kelvin-Helmholtz and Rayleigh-Taylor kind of a model for secondary breakup, okay, is once again let us not go through the math once again. This is once again the K max, which is the maximum K, this is the corresponding maximum growth rate. Both of these are given in terms of the gas phase Weber number, as you can see over there, all right. So, these are the, once again it is cast in terms of Weber number, and the taus, that means the breakup. If you recall what is called a back breakup and what is called a shear breakup, if you do not recall, let us just go and show you the picture once again to recollect from memory. So, this is like a back breakup that we saw, right, okay. And if you have forgotten even now, so this is also how the phenomenologically a back breakup actually looks like, right, okay. So, based on all these things, so this is for the back breakup and this is for the corresponding shear breakup that you have, okay. So, both of these are written in terms of Weber number and Onsorge number, and the breakup times also you can calculate. So, basically this serves a lot of purpose, okay, that you can know from these expressions, okay. These are, let me remind you, this does not include any effect of swirling flow or any other complicated flow dynamics, okay, which happens in real life. This is a pure jet, a liquid jet that is coming out in a pure uniform flow field. That is how this is modeled, okay. So, let us not get ahead of ourselves and think that this is something else, okay. So, this is just a pure liquid jet that is coming out in a coaxial liquid flow. So, there is no swirl, no tangential component, and all of those things have been neglected in coming up with these expressions, but they are surprisingly powerful because they enable you to calculate, right, that what will be the, for example, the droplet diameter or the time scale, back of the envelope calculations you can quickly do, okay. For your real life situations you might have to do a more sophisticated simulations, okay. These are not sophisticated, these are pure linear stability analysis, okay. So, these are workarounds, right, because ideally if you want to really predict the droplet breakup and other things computationally, you need to do something like the volume of fluid or level set kind of things, okay. So, essential role of the wave model is to find the most unstable wavelength and correlate it with the droplet size. So, that is all that is there in this, right. So, let us assume that this is all that you have to know about the wave model, and it does a fairly good job about it. Now, before we end this particular discussion on atomization, okay, so let us revisit this figure that we said once again, and let us look at the different stages. So, what happens is that in most of the applications the droplets do not come out as droplets. First there is a liquid sheet that comes out, okay. Whether this liquid sheet forms outside the nozzle or inside the nozzle, that is subject to the nozzle design, whatever nozzle design that you are kind of pursuing, right. So, one needs to predict. So, there is a common misnomer that, oh, I know what droplet sizes are coming out of the nozzle. That is incorrect, right. In order to predict what droplet sizes is coming out of the nozzle, okay, or after certain distance away from the nozzle, right, one needs to actually know that the droplet atomization mechanism, so to say. So, in this case most of the atomization mechanism will be that you are going to actually have a liquid sheet. This liquid sheet you impose some kind of a disturbance, or that the disturbance naturally happens because of the difference in the flow rate, or the difference in shear, because of the shear, and there is a wavelength that actually starts to grow over this liquid sheet. If you look at the PPT over here, you will find then you have this sheet on which there is a disturbance that has been created. This liquid sheet immediately comes out and breaks up into these ligaments. This is called fragmentation and formation of ligaments. So, the formation on waves on the liquid sheet is what that Kelvin-Helmholtz type of instability is. Then this forms actually these ligaments on the surface. These ligaments actually detach. So, these are like cylinders. These cylinders further undergo oscillations that can be Rayleigh-Taylor, it can be Kelvin-Helmholtz once again. Okay. These cylinders that you see, this particular cylinder, if you concentrate, you are developing these oscillations on the surface, right, of the cylinder. The cylinder then after that undergoes this kind of breakup, okay, and they form actually these dotted droplets, right. So, it is breakup from ligaments into droplets. Up to this the KH instability is particularly powerful, right. Even when this droplet actually forms, these are nice and round droplets sometimes, okay, they still face this aerodynamic load, right, around it. So, these droplets can actually undergo that kind of breakup, which is basically like the tab. So, the tab model is good in the case of secondary breakup. Okay. These droplets however can also undergo oscillations like this, right, and then it can actually split. So, that will be more like KH or Rayleigh-Taylor or something like that, got it. Okay. So, there are two pathways basically. So, it depends all on the droplet size, because your Weber number is proportional to the droplet size, right. So, if your droplet size is sufficiently low after this stage, after the primary breakup stage, okay, if it is sufficiently low that its Weber number is actually low, okay, you can use the tab model to predict the secondary breakup. However, even after this breakup is over, if you see that the Weber number is still very high, you can get this secondary connotations on the droplet surface, and you can get this secondary breakup through the KH or the surface active modes, right. But there will be a certain size at which the droplets Weber number will be sufficiently low where you can use the tab model at that point. Okay. So, this is basically a hierarchical or a sequential modeling. First you do KH, then you do KH once again, right. Then you can have a bifurcation, you can do KH, then you can go to tab, or you can directly go to tab. So, this will be for Weber number greater than actually here Weber number greater than 11, this will be for Weber number less than 11, right. This is basically the sheet, this is basically the ligaments, got it. That part should be clearly understandable, correct. Okay. So, you can also find out, say for example, so by simple math that the mass conservation between a jet and the droplet, you can find out for jets what will be the droplet diameter. So, the droplet diameter and the corresponding perturbed jet cross section. For liquid sheets, you first balance between the liquid sheet and the ligament, and then you balance between the ligament and the droplet. So, when it is liquid sheet is like a sheet, right. So, it is given by pi dl square into this, actually this is given by T into the corresponding lambda, and then you correspondingly get a ligament. Ligament is like a cylinder, right. Okay. So, you can get it from the ligament, that particular thing. Okay. So, L cancels from both sides, and then you get a balance. So, this is a balance between the liquid sheet and the ligament, right. Then from the ligament and the droplet you get another level of because that also has this wavelength, right, on the top of the ligament surface. So, from there to the drop, okay, you can add another mass balance. So, simple exercises. Okay. So, whether it is a jet like this, right, or whether it is a sheet like this, whatever is the configuration, most of these falls within these two configurations, we can actually show this. The work is from Lec34 in 1989 particular paper, right. So, this we have already shown how to find it out, these cases, and these are the references that you should study. Okay. A lot of these are in physics of fluids and experiments in fluids and JFM, Journal of Fluid Mechanics. So, it is recommended that you study all of these papers in kind of details. Okay. So, I think you have given a nice idea that a jet breaks up, a sheet breaks up, a sheet breaks up into ligaments, ligaments breaks up into droplets, droplet breaks up into smaller droplets, right. This mechanism is either KH or you can predict it by the tap, depending on which end of the spectrum you are, and there are other sophisticated models on the top of that makes basically fine tuning. Okay. In the case of a jet, exactly the same thing happens, first is KH and then from the drops you can have tab model or other such models. Okay. Enhanced tab, there is enhanced tab and other types of models, okay, which basically are more sophisticated in nature. Okay. How do you model the KH instability? Just by doing a linear stability analysis. You can include the effect of viscosity, you may exclude the effect of viscosity, right, because viscosity is like a damping kind of a system. Okay. So, as we said, some wavelengths can be actually damped. Okay. What we want to do through the KH instability, we want to find out the maximum growth rate, the most unstable wavelength, the breakup time scale and the dotted droplet diameter. If we have all this information, then we can predict what will be the sizes that will be coming out. What was the tab model? Tab model was a vibrational model, essentially 1 degree of freedom, which predicted what will be the droplet diameter just by treating the droplet as a spring mass system, underdamped spring mass system, right. So, that is all that we did. These are the two basic classes of models. There are a lot of other models also, more sophistications, okay, but these are very analytical, so that you can get a feel of what is actually going on, right. For example, in the KH, you know that there is a disturbance that grows on the surface, this disturbance just gets amplified, and as it gets amplified, it just actually snatches or just extracts the droplets from the peaks of those waves, from the peaks of those waves. Okay. So, these are very important for the understanding that why atomization is important, what kind of atomizations we can have, what are the different classes of atomization, that also we covered bag, shear, vibration, a lot of modes of atomization. Okay. So, we end here in this particular topic, okay, where we have covered all this whole gamut of activities, okay, including there is some math which you may want to do in your spare time, right. But the basic governing equations we have written, we have also shown you examples that what are the different types of breakup from our own experimental data and what will be the corresponding time scales, how to determine these constants in the case of a tap model and things like that, right, what kind of a study people actually did. Okay. So, all these things will become very helpful when you actually go to the next level. Okay. We also showed that when Onsorge number starts to become important, Onsorge number is a viscous effect, we saw that it only becomes important kind of after 1 roughly, okay, so to say. Okay. So, and we defined what Weber number is, once again there is a D over here, okay, so that you should remember, and this also has a D. Okay. So, the Weber number is the key important parameter, always keep that in mind, Weber number is the most important parameter, right, most important parameter in whatever you do, right, and Onsorge number basically takes into account the Weber number and the viscosity, right, and the surface tension, all of these things combined. So, and most of the maps will be done by Weber number. We also had a good discussion on how the spray formation actually happens, that there is a primary breakup zone, there is a secondary breakup zone, all these things. It's a very complicated dynamics. We have not covered, for example, the droplet flow interaction cases. That would be very interesting to see, but that is not a part of this course. Maybe in some advanced course we can look at that particular thing. Okay. And we also showed some videos. If you want to play one video once again, we will do that. But we have to come out of this mode, I guess. So, you can see the videos once again, okay, primary breakup essentially, and if you look at it, this will be the secondary breakup. Okay, the droplets are not spherical, but they do become spherical further downstream, where we can apply all this droplet evaporation model that we covered, right. Okay, so with this we end this particular lecture. We are going to go and look at droplet combustion in some details now. Okay, thank you.